Hello guys, this video is about LNA simulation, low noise amplifier. It's an RF block in the receiver chain. So this video will help you from the scratch to the complete details of simulation of an LNA, but this will not help you in designing an LNA. Right? That is a big theory, aspects, design procedure, everything has to be covered that are explained in textbooks. But this will help you with simulation of LNA, proper simulation of LNA in Cadence. All right. So as we all know, LNA is a low noise amplifier block which goes to mixer. So the inputs for LNA comes from antenna. Antenna receives the signal that is being transmitted from somewhere else. It receives the signal. So the signal that is received here will have low power level, some very low dB in negative -x, let's say. So the noise of this thing and the amplitude of the original signal, the noise that this signal catches during the transmission or the noise from the transmitter itself, both of them are in comparable levels to this. So we don't want to add additional noise in our path. And if you look at the freeze equation, the noise of this LNA, the first block in the receiver chain, directly adds up, plus the noise of the other thing, amplification, gain A of this thing, NF of mixer, so on from the freeze equation. So this LNA should have very low noise. That is one of the reason. That is why it's called low noise amplifier. And the signal from antenna goes to LNA. And antennas are matched to 50 ohms. 50 ohms. That is the reason people ask us to match LNA to 50 ohms. There is no requirement for matching here. When you are directly connecting the LNA to a mixer in your IC, you don't have to match anything because this is inside an IC. There is no matching required. Unless you are taping out to the LNA, then only then you need to think about the specifications of matching and all. But when the LNA is directly connected to mixer in your IC or in your design, you don't have to think about matching. So this need not be matched to anything. Okay, to an extent it is clear on why we need to match it. Now the question is about how to include the loading aspects of this mixer in this LNA. Typically the LNA loads are LC tuned at high frequencies, and this is resistance of the tank, which can be parallel resistance, because parasitic resistance of the LC network, and in additional you can put some more resistance for this, right? So, and this is connected to mixer. Mixer is typically, let's say, Gilbert cell mixer. It is the MOSFET gate looking in, Z looking in from this gate. This output of LNA goes to the input of mixer, which is gate of a MOSFET, Z looking in. So this will have parasitic capacitances, all typical parasitic capacitances from gate to source, gate to drain, gate to bulk, etc. CGS, CGD, CGB, etc. So to use a simplified model of gate looking in, I will say it as CP in parallel with some RP, because there is some resistance when you look into the gate, but typically this resistance is very high, something in kilo ohms, and this is typically in femtofarads, or because of the parasitics of this. These both things are dependent on the process, but nevertheless you can simulate the looking in capacitance and resistance of this by connecting a port. You connect a port, your simulation, and then bias this. Let's use some mega ohm resistor, bias the MOSFET properly with VDC, And for this connection, use some large capacitance C large for biasing and connect it, and bias it with again some DC at the drain, so that this MOSFET is in saturation. And you do S parameter simulation in Cadence. Plot ZP or ZM, anything that you want. Plot Z11 real and imaginary parts, less imaginary parts, and you calculate the real and imaginary parts in this, equate the equations, back calculate the values of real and imaginary parts, and you make it an equivalent circuit. So for that purposes, people usually include some additional C L, let's say C load at the load of the LNA that comes close to this. So they will have some additional capacitance when designing the LNA itself, so that the parasitics of this can be observed in this. Suppose let's say my CP finally comes out to be some half of the CL that I have used here. So after I integrate my LNA with the mixer, I will have to change the CL, the load capacitance that I have put in the load of my LNA, to half of CL, right? This will be my load of LNA, and the another half of CL comes from this mixer looking in. So that is the reason you always design LNA with some buffer capacitance or with some additional capacitance at the load. Now let's jump into the simulation of LNA. Alright, so ignore the specifications here, only focus on the simulation process. So this is my common source LNA differential, and let me highlight net highlighting. So all the bulks of MOSFETs are connected to ground, we did here, and this capacitance I have put it as 1 picofarad, so that if there is some capacitance from the mixer that I interconnect this to that later on, I will reduce this capacitance and the overall function is good. Put a cascode block for low noising thing and good gain. This inductor is used for tuning. This LNA is designed to operate around 2.4 gigahertz. Alright, I have put enough number of pins. Now this LNA is ready to test. Right, oh, this is the symbol of LNA that I have used: V in plus, V in minus, VO plus, VO minus, V in plus, V in minus, VO plus, VO minus, VDD, V bias of cascode, and V bias of the amplifying stage, this stage, V bias here, V bias of cascode here. And these are the capacitors for biasing this circuit. Right, I have used some large capacitors. These are large capacitors for biasing. And now I have a balun. The balun properties are this. I used RF flip balun, and the balun properties are input impedance 50, balance output impedance is also 50. So this port will see 50 ohms from this, all good. Now both of these ports expects 50 ohms looking in from this, and this port will look 50 ohms from this only when this is properly matched. And at the outputs also have done the same thing, similar thing. and I have put a port here for testing. This is at the load, so 50 ohms, done. And this is at the input, 50 ohms. I have to give a frequency, FRF, frequency of operation, amplitude, PRF, I have given PRF. Initial phase I have given at 0 and DC fine 0. So this is the input, this is the output side. Okay, and there is a small mistake in this whole simulation process that I will detailedly explain in the end. This is about the gain of the LNA. This setup will hamper your gain, and that I will explain at the end. But for now, let's proceed and do the simulations. As parameters, I'm selecting the ports. Port 0 is input side, port 1 is output side, and I'm simulating from 2 to 3 gigahertz because my operating frequency is 2.4, and I'm opting to do noise. Output port, select output port, selected, port 1. Input port, this is my input port, right? Apply. Okay, done. Looks good. And if you have noted, this port impedance is set as 50, and this port impedance is also set as 50. Only then it will make a sense that S21 is gain. If this port impedance is not 50, is not set as 50, the S21 will not be equal to gain. Right? That is explained from the fundamentals of S parameter networks. That is explained from the fundamentals of S parameter definitions. That is explained in another video. You can see it here. Okay, starting the simulation, and it's done. Results, direct plot, main form, SP, S parameter, rectangular. Let's plot DB, S11. All right, S11. I am putting horizontal markers. S11, it's minus 10 from 2.344 to 2.63. So good, around my 2.4 gigahertz. My S11 is less than minus 10. Good enough. S21. For S21, my gain is around 19 dB, around the frequency of operation, and that is also good enough for me. Now we can also plot noise factor, NF, noise figure. NF is noise figure, and let's plot dB20. You just have to click on this plot because you have already specified what is the input and output thing. Plot. Noise figure is some 657.41 milli dB. Okay, I want to see noise factor. So in that case, close it. You just have to do a different simulation called noise simulation. Frequency 2 gigahertz to 3 gigahertz. Linear number of steps, let's say 500 again. Output probe, this is output probe. Input port source, this is input port source. Okay, yes, simulation is done. Results, direct plot, main waveform, noise. Now you can see several things here. Noise figure, noise factor, you can plot and enjoy everything. Noise factor, plot. Noise factor is around this. noise figure plot. Noise figure is like this. It's less than 725 milli dB in my entire frequency range, and noise factor is like this. You will get in volt square per hertz, just for your enjoyment if you want to read that value also. All right, this is about gain, input matching, noise figure. We have seen three things so far. Now let's just also see the looking in impedance, real and imaginary parts, for our satisfaction. Results, direct plot, main form, and you must see Zm, not Zp. Zm real parts, Zm1 imaginary part, Zm1. As you can see, the real and imaginary parts around 2.4 gigahertz. It's 67 real minus 20 imaginary, and the imaginary part goes to 0 around this, somewhere around this, around 2.5 gigahertz or so. But even though the real and imaginary parts are like this, my S11 is good enough so that I can proceed from there. But if you want to pay good attention to real and imaginary parts and match it exactly to 50 plus J0 as impedance, you have to look at Zm1 real and Zm1 imaginary, and then appropriately match your network, appropriately tune your inductances and capacitances or whatever that you have used as matching network to make it 50 plus I0. That will give you the best S11. Now let's do 1 dB compression point. We will go to HB simulation, fundamental frequency 2.4 gigahertz. As you can see, I have given 2.4 gigahertz here. This port has 2.4 gigahertz thing, and the amplitude 1 dBm power I have given it as PRF. Now we have to sweep that PRF to a certain range to plot 1 dB compression point. Right, select design variable PRF. Let's sweep from minus 60 to 5. Number of steps, this is 65, so let me give 130. Apply. Okay, 2.4G. Apply. Okay. Done. Let it run. It takes a little bit of time to get the simulation done. You can nevertheless go for less number of points, let's say 65 points itself, or you can use moderate level of simulation. You can use moderate for quicker thing, or you can go for lesser number of points here. You can see the number of points, the point that it is simulating it here, 127, 128 and 130. Right, it is done. If you pay little attention to this, you will understand what is happening in each of the sweep. Results, direct plot, main form, HB compression point, select port, fixed R port. This is our fixed R port. Format output power, compression point, input referred compression point, P1 dB, and gain compression 1 dB, input referred 1 dB compression, which is going to be plotted. And now select a point for extrapolation. I am selecting minus 50, and the first order harmonic is 2.4 gigahertz. Now I need to select port on the schematic. Done. My 1 dB compression point is here. It extrapolates the curve from here and measures where the power goes 1 dB lesser than that. That's the meaning of P1 dB. My P1 dB is minus 18.9277. Close. Alright, this is all about simulations. Now let's get to the main problem in this simulation with the gain. With the earlier setup, if you are getting very low gain, then there is something that you need to really look at and take care of. For that, let's do a couple of tests. Now I'm going to try out AC simulation. DC current 0, AC magnitude I'm giving it as 1. Now I'm going to pump current into this node. Right, this is an LC network. There is some parallel resistance to it. At resonance, the total impedance that this node sees, or that is looking in from this side, the total resonance at this point, let's also name it. Let's name it as out. So the total resonance seen at the output or out node is 300 at resonance, where the imaginary parts cancel out because of the inductance and capacitance. J omega L minus 1 minus J by omega C. Both of them cancel out at resonance. Right? Let's launch. Let's click AC simulation. Frequency, let's start from 1 gigahertz to 6 gigahertz. Linear number of steps 100. Since the current here is 1 amperes, 1 ampere AC, so it is 1 ampere for all the frequencies. So this current is being pumped into this load. Right, let's observe the voltage. Simulation is done. Results, direct plot, main waveform, AC voltage net magnitude. Yes, you can clearly see there is a peak, and that peak is close to 300, very close to 300. If I put it exactly at the resonance point, 299.99, 2.4 gigahertz. So this 4.4 nanohenry 1 picofarad capacitor will resonate at close to 2.4 or 2.4 gigahertz, and the value of voltage there is 300 because I into Z at resonance is 300, right? And this plot looks a bit similar to the impedance of a parallel resonant network, right? Peaking at resonance. All right, now let me put a port here, port, and the port is 50 ohms. This port is 50 ohms and DC, let's say. Main form, AC voltage magnitude. You can see what happened now, right? The total voltage or the maximum voltage now is 42.85, which means it's similar to 300 parallel 50 ohms. Or to make it more clear, right, the same test bench. Okay, now let's try and do the simulation. Yeah, simulation is done. Main form, AC voltage. You can see both of them overlapping, which means the addition of this port with 50 ohms now has brought the whole impedance to be 300 ohms in parallel with 50 ohms. Earlier it was 300, now it is something around 42.5, which means the overall impedance, the real part of the impedance at the resonance, or the overall impedance, has now gone down to 300 parallel 50. The same thing happens when you put a port directly at the load of your LNA and test it, right? S21, the overall impedance goes down to be 500 ohms in parallel with whatever parallel resistance that you use at the load of the port. So the best way to counter or tackle this is to do this. to introduce a vcvs between the output load and you bring a vcvs here, vcvs vcvs of gain 1 voltage source has two inputs plus minus. These are the inputs and these are the outputs. So what this brings out is that there is an isolation between this port and this load now. Now this load will no longer impact or reduce the overall resistance of this point. Okay, so the input looking at impedance of the vcvs is infinity. It's an open circuit. Now let's do the same test. And you can clearly confirm the voltage now is 300 again. Back to the same thing, and you can do the same S21 simulation, right? We can test this also. I have an LNA schematic here. Now the input is this single-ended LNA. This is one side. The input port is this. Output port is this. Now I'm going to do something like what is done earlier. I'm going to introduce a vcvs and see what difference it brings to the overall circuit performance. Okay, and let me also mention you one thing again. The impedance of this port, input port, is 50. So the impedance of this port should also be 50. Only then the S21 will be equal to gain. Otherwise, it won't make any sense. Let's select the ports. Port 1 is labeled as port 0, is the input of the left half or left side LNA. Port 1 is the output of the left side LNA. Port 0, port 1. Port 4 here is our port 3, third port here. Port 5 is our fourth port here, which is the output of the right side LNA. 2 to 3 gigahertz, same setup. Let's run it. Results, direct plot, main form, SP, S21. Okay, we have plotted magnitude. Let's look at dB, S21. And now let's plot S43. Port 2, this is port 1 gain of this network. S43, this is port 4, this is port 3 in our simulation. So S43 will correspond to the gain of this network where we have put a VCVS. Right, S43. This is the difference. You can see a 17 dB difference, approximately 16 to 17 dB difference. Right, which means, and which also confirms the same setup I have took 4.4 nano, 1 pico, 300 ohms. This is 50 ohms port, which will eventually load this. The overall resistance of this load will become 46 point something. Now this is, whereas this has 300 ohms as the load, right? So when you interconnect this LNA, make a differential copy of it, interconnect with mixer. Mixer has some capacitance which you have to absorb in this. So if the mixer looking in capacitance is 0.25 picofarad, you make it 0.75, interconnect it, and the gate eventually will usually has larger impedance. It doesn't have 50 ohms. So that will be in some, let's say 5 kilo ohms or something. So that will be 300 in parallel with 5 kilo ohms, which is very close to 300, which will not make bigger impact. So the overall thing is okay. So I prefer this way of doing simulations for, so that the gain will be better. I mean, the gain that you simulate is actually close to the gain that you get. You can even confirm with the AC simulation also. Okay, that we have did a test. So if you have to do the same test here, what you have to do is replace this port, put a VDC, and AC magnitude, give it very less. You have to give it somewhere less than far less than 1 milli, or the amplitude dBm that we have seen, our P1 dB is minus 20, right? So you have to give inputs less than minus 20 with respect to 50 ohms. So let me give 1 nano as amplitude for this, and you connect it to this, do AC simulation, plot AC gain from here to here, output to input. You will observe the same thing being happening, 20 dB, 40 dB, 36 dB kind of thing, right? This is one important thing to know. So where should you put a vcvs here? Now you can put it here at this point. You break this up, put a vcvs here, fine, or you put a vcvs here, fine, it works. Okay, you put it somewhere before the balun, before this cap or after this cap, and do the gain simulation. It will give you much appropriate or proper result. Okay, uh, that is the reason why most of the people get different gains, or the gain will be suppressed. Most of the people see the gain being suppressed when you put a port of 50 ohms and see S21, and when you remove the port and when you usually do AC analysis and plot the gain, this port loads the output node. This video covers all things about how you plot the gain, how to properly plot the gain, and the loading aspects of the port or the mixer, how the mixer will load your LNA, and how you can accommodate those things. And you have seen how to properly do IIP3 simulations, P1 dB noise, right? So I have shown noise and noise analysis through noise simulation and SP simulation. There is another way of doing noise, HB and HB noise. You have to run both HB and HB noise simulations, so that what happens is that in noise and SP noise, the entire network is linearized around the operating point and the noise is calculated. Whereas in HB and HB noise, it does the large signal noise calculations. Okay, it doesn't do the small signal noise thing. Whereas this noise and noise in SP analysis linearizes the whole model around the DC operating point and does the calculations. This doesn't behave that way. The setup is same. Just select the frequency, range, sidebands, and noise figure, output probe, do it. Right? We don't anyway need noise simulations for large signal. We are anyway focused on small signal things. So SP simulation noise, or individually do a noise simulation, that will help you solve the purpose. This noise simulation or SP and do noise, yes, that will work. Yeah, this is the end of whole simulation process for LNA.